let's try to solve this problem here. Suppose a monoatomic ideal gas, so this is a monoatomic gas, is changed from state A to state D. So it goes from state A, which is this dot over here, to state D, which is this dot over here, by the process shown on the PV diagram above. But if you look at this diagram over here, we actually don't see any line, any arrows, right? All these are dotted lines, so these are not actually the process. The process is not yet indicated on the PV graph. What we are seeing here is just 5 different states, which are A, B, C, D, and E. There are 5 points on the PV graph, which shows 5 different states of the gas system. But it goes from which state to which state, and we know it goes from A to D. But how does it go from A to D? Whether it goes to B first and go to D, or it goes to E first and go to D, or go to C first and go to D, we are not sure yet, okay? But let's look at question A right now. Calculate the total work done of the gas when the gas follows the constant pressure path. So from A, what happened is, from A, you undergo a constant pressure process. Constant pressure process is an isobaric process, so the pressure must be kept constant. So initially, if you are at 2 atmosphere, then you have to be kept constant at 2 atmosphere. That means by your process has to be a horizontal line on the PV graph. So if it's a horizontal line on the PV graph, you know that the next destination will be point E. So you'll be going from state A to state E first. Okay, then you say followed by a constant temperature path. So once you reach point E or state E, what you do is you next undergo an isothermal process. Isothermal process temperature must be kept constant. So the process must be happening on the isotherm line, because every point on this line here will share the same temperature. And because this process that you are going to undergo here is a process that kept the temperature constant, so the process must be happening along this line over here so that the temperature can be kept constant. So we know that the line will be going from E to D. Okay, so it goes from A to E, then afterwards from E to D. So let's so what are they asking for? They're asking for the total work done. So how do you calculate it? You can first you can actually determine the area under the graph over here, find this area under the graph, then after that find this area under the graph. Then essentially you get your total work done for question A. Okay, but we know the equation, so we are not going to go through the integration process. So we are going to just write as work total is equals to the work done from process A to E first, followed by the work done from process A, from state A to state D. So from state A to state E is an isobaric process, we find the work done. Then after that, from state E to state D is an isothermal process, we find its work done as well. So for A to E, you know that it's an isobaric process, so the equation that is suitable is P V final minus V initial. But P, any pressure will do, either A or E, they have the same pressure, which is 2 atmosphere, so you can just write either one of them, pressure A maybe. Then you take final minus initial. You're going from A to E, so A is initial, E is final, so V final, final is E, V initial, initial is A. Okay, so that's for your work done for AE. Next, you have your work done from state E to state D. So this is isothermal. Isothermal, you have to use nRT. Temperature, any temperature between E and D are the same, so you can use any temperature, let's say D. Then you can use ln. Then you have your volume final. Final is D, initial is A. So volume final VD divided by volume initial VD. Okay, so once you reach this stage, what's your next thing to do? Your next thing to do, well, if you notice, we don't have number of mole in this situation. So again, if you don't have number of mole, one thing you can do is you can substitute nRT to be replaced with PV, which is what you know from ideal gas law. So nRTD will be equals to PVD VD. Okay, you can also use PE VE, that's fine as well, because we know that the temperature for E and the temperature for D, they are all the same temperature. Okay, so I'm going to use D over here. Well, for no specific reason, I'm going to use D over here. Okay, so maybe PD VD ln VD over VE. Okay, so I believe you have all the values, so it's just now substitution. So 2 atmosphere, you have to convert it into Pascal. So 101,325 to convert it to Pascal. Then volume is in liter, so make sure you convert it to meter cube as well. Volume of E. E is 8 liter, so convert it to meter cube times 10 to the power negative 3. Volume of A is 4 liters, so minus 4 times 10 to the power negative 3. So from here you get your work done for process AE. Let's continue. Then you have pressure D and volume D. Pressure D, as you can see, is 1 atmosphere, so that's 1 times 10 to 1 times 101,325. That's your pressure at D. Then your volume is 16 liters, 16 times 10 to the power negative 3. So this is pressure and volume. Then you have your ln VD over VE. Okay, VD, volume for state D, volume of state D, 16 times 10 to the power negative 3. Volume for state E is 8 times 10 to the power negative 3. So you have everything figured out, everything substituted in. So now you're just left with calculation. And I believe if for the first term you get 810.4, for the second term you get 1123.5. So if you sum them up, you get the total work done to be 1934 joule. Okay, so everything here is positive because it's expansion followed by another expansion. So it's always going to the right in this graph. So this area here is positive, this area here is also positive. Both areas positive, so the sum of them will be a larger value, which is 1934 joule here. Okay, if it involve another process which go in the reverse direction, then probably the work done will be negative. But no matter what, it's just the sum of all these processes, the sum of work done for all these processes, then you find the total work done. Okay, so that's it for this question. Thank you very much.